COLDSTEEL Sprite Studio Devlog 1. COLDSTEEL Sprite Studio is a pixel editor in which users can create images and graphics. It's targeting game developers, as it will include features that game developers may enjoy, such as animations and paletted images. However, Sprite Studio doesn't necessarily have to be used for game development and is architected to work for general purpose raster graphic creation. As for the code of Sprite Studio, it's written in Java 17 using the LWJGL library for rendering and UI, among other things. However, I've written a thin general purpose wrapping library over LWJGL, which abstracts some of the tedium and some of the low levelness of some of the libraries LWJGL gives access to. All that said, let's start by running the program in Eclipse IDE to see what exists right now. Okay, so when we run the program in Eclipse, the application opens in a window which we can resize or toggle full screen. So we could hit F1 to go into full screen, or in the options menu we can toggle it. And as we can see, there's three main UI elements to look at right now. The left panel contains tools used to actually modify pixels, and the right side shows the project hierarchy. And these may change a little, but I like their simplicity, to where the left-hand side contains stuff used to modify the artboards, and the right-hand side just shows you basic stuff about the project you're working with. Now, to start editing something, we need a project. So to create one, we go to the project menu up at the top, click new project, and from here we can basically customize our project. We get a new project menu. The first few options have to do with the way color values are stored for the project. These are kind of global in the sense that all artboards associated with the project will have these settings. The first is a checkbox about whether to use paletted rendering for the image when it's exported. And to be honest, I'm not entirely sure how this will work. For example, when we have the paletted rendering checked, should we export the index texture and the palette texture separately? We'll see, but likely I'll give a couple of options for people to choose from. But after we've selected that, next we select the number of channels. So this effectively allows us to choose whether we want grayscale or color, and whether we want transparency on our image. So we'll choose 4 channels. And the next option has to do with how many bytes each channel should take up. The widely used standard is 1 byte per channel. So if we have a 4-channel image with 1 byte per channel, we basically have a 4 byte per pixel image. And finally, we can name our project, and we have a blank project ready to work with. And we can see that once we create our project, our right-hand panel has changed. It now shows our project, and we can expand this drop-down to reveal some more stuff about the project. There's a few things here, such as animations, non-visual layers, visual layers, and I'll show some of that stuff off later because they're mostly placeholder for now. But just to demonstrate them, I will make an animation. But we can see that when we drop this down, nothing appears. But if we go to project and add animation, we can create an animation. And once we do that, it appears here. But nothing else happens, and it's just placeholder, obviously. But if we actually want to start editing something, we need to go to add artboard. And here we can create artboards of any size. So for example, I'll make one of 100 by 100. There it is. But we can make these different sizes, so I could go for 10,000 by 10,000. And we can do that as well. So to edit our artboard, we use the left-hand side panel to choose a brush type and set it up to fit our needs. So typically you might go for the pencil brush, and using this color picker we can select a color to use. And in the options menu, we can actually adjust the camera move rate, and that's in pixels. So that way, it doesn't take all year to get across to this big artboard because it's pretty far from the first one. So yeah, you'll probably be able to move these in the future, but as of now, they just kind of basically get put far away from each other. But once we have our pencil brush selected, we can actually begin to modify an artboard. So if I click, we can color it in. What's interesting about this is the fact that it's pretty laggy. As you can see, when I move my mouse, the pixels are very delayed, but that actually doesn't last very long. And you can see that now it's back to real-time speed. I don't know why this is. It seems to be some sort of just-in-time compilation, but I don't know. We can also adjust the brush size, allowing us to color in regions of the brush, of the artboard. So the radius is like it's a radius from where you clicked from. You can see we can also do whatever we want. We can pick a different color, etc. And just to demonstrate, we can click the eyedropper and click on a color, and we have now reselected that color. And we also can use the replace all. The way that this works is whatever color I click on, every pixel of that color will be replaced by the color that's selected in the artboard, or in the color picker. So if I click it, it just replaces everything. And we can also undo stuff. We can undo anything up to a limit. Now we also have these buttons here where you can actually input the color values as hex. So for example, I could get an exact yellow here to where now that's yellow, or it kind of looks like yellow. It's hard to say. Or we could go for white, for example. Or we could go for any color in between. Some sort of random color. So we can do stuff like this. It's pretty basic. We can actually see that our artboards are in this drop down as well. And you can actually expand these layers here. Currently, layers don't do anything. They're very much so placeholder, but that's kind of what's next to add in, and I will show that more in the future. But that's largely what this application is right now. But what I want to do is take a quick look at the code to try to show how all this actually works kind of under the hood. So you can actually just go to File and Exit to close the program. And I think the main classes to look at for this program are the engine, the artboard texture, the artboard palette, and the editor. First though, let's start with the main method, obviously. This is the main method. As you can see, it's pretty simple. It's inside the launcher class. It has a static pre-initialization, which takes the arguments, then creates a single instance of engine. So we can take a look at the first method to see how it works, though there's not much to it. We basically create an array list that takes in the arguments and then parses them out. I see there's only one argument right now, -d. If it's enabled, if it's present, we enable debug mode. And all that does is enable the debug memory allocator that's part of LWJGL, so we can track memory leaks. It has to happen before anything else happens because this configuration must be set before any memory allocation or it will not work, as far as I can tell. The only static members of the engine class are the thread pool and the temporal. The temporal is essentially a scheduler object. You can pass code to it and it will only do it. It adds some sort of predicate to calling that code. So we go back to the main method. The first thing we do is construct an engine. This is probably the most important part. Yeah, so within this, we first create a CS display object right here. So to understand this, prior to beginning writing Sprite Studio, I spent about 2 months on a library I call COLDSTEEL Core. And this is basically a thin wrapper over LWJGL, an abstraction. I made it according to what made sense for me. So some parts are higher level than others. Some parts are thin wrappers. For example, GLFW is very thinly wrapped, while the nuclear abstraction, which is the UI library, is very high level by comparison to raw nuclear. But we create a display which basically contains a window, a renderer, a camera, and a UI factory. All of these parameters are used to set that up. Yeah, so after we create the display, we actually initialize the artboard shader. The artboards are all rendered with one shader, and we can create many artboards, but each of them uses one shader, so we have this static artboard initialization. Right, so the shaders are actually a bit more complex than a simple pass-through of a texture because they're paletted, so we actually have two textures, which is the artboard texture and the artboard palette. And the artboard texture contains indices into the artboard palette, so it's a bit more complicated, and the shader does the logic for that. I may show it in a moment. After that, I set up a very basic system for program controls. Controls like things like move camera, activate artboard, undo and redo is very simplistic. What this basically does is set callbacks for whenever a key is pressed to check whether it's a mouse key or a keyboard key, and then to call the right window function or the right GLFW function to check it. We then create the editor, set up some OpenGL stuff, and set up some peripheral callbacks down here. So for example, we set up blending and different stuff about OpenGL blending. Here's the window callbacks or the keyboard callbacks. And at the end of the constructor, we call a method called enqueueRender. So the rendering abstraction I came up with for OpenGL is a highly event-driven one. You post code to the render thread to execute. In fact, if this parameter right here were true, then the renderer would run in its own thread. It actually is set to false right now, but I will go back to making it true in the future. But if it's false, then the renderer runs in the calling thread. So the renderer thread is the main thread right now because this is false. But if this were true, then it would be in a different thread altogether. And we can access the renderer from the display as a public member, calling its post method to push code to it, and then the thread will invoke that code in a kind of fair way. If we go to enqueueRender, what we'll see is we have the first part lays out the user interfaces, so it actually calls all the code to lay them out. Since nuclear is kind of an immediate mode UI, we call its functions every single time we want to update them. Next, what we have is a thing where we assign a variable called render scene to a post. Effectively, this is a object that allows you to track an asynchronous event. It's called an await. So we call this render post, it returns an await, and this code will be invoked on the render thread. And we can use the post method to post this event to the thread, or to the event system from the renderer. And then this is used to track whether or not, it tracks a few things. If I actually open the declaration, we can, well, we'd have to open the declaration of await, but in general for this, we call the render scene method, which just calls enqueueRender if the render scene is finished. So one member of render scene is finished. If it's true, we re-enqueue, essentially. So right above render scene, we have the run method. This is essentially the update. It updates every time, or this is what continually keeps the application running and updates it. It's just a while loop. So while display.persist, which effectively checks if the window should continue to open, which is a GLFW thing. Once we're in this loop, we wait for inputs, which is the wait inputs method. And what this effectively does is lock up the application until an input is detected from the mouse or keyboard. Once any input is posted to the program from a peripheral, this method returns. We then go to control events. What this basically does is checks what controls are pressed based on what peripherals are, or what peripheral events are posted. So, for example, the F1 key is used to toggle the full screen of the application, and toggle full screen is a control. So this method would check whether F1 is pressed, and if it was pressed, it would call a function to basically toggle full screen. The next two event updates here are editor functions or editor methods, and they are based on the editor, which we'll be showing in a minute. They effectively, the first one reads the controls, like what I described with the control to toggle full screen, and it populates the editor's event queue with, well, it's more of a stack, but it checks the controls and adds events. The next one handles events, and we can see that it actually takes the renderer, which is just a method on the engine class, because some editor events, or some events like events that modify the artboard, have to be put to the renderer thread, because OpenGL code must be called from the renderer thread. At the end, we update the temporal, which effectively means anything that was, any code that was given to execute within a given time frame, or with some predicate attached to it. We'll check the predicate, and if the predicate passes, we'll handle the event. So it's highly event driven. The advantage of event driven things in this case is the events just have a do and an undo method. So we'll show that later, but it's very convenient. You do something, you put it on a stack, and then if you undo it, it just calls the undo method and puts it on a different stack, which we'll show that in a minute. But that's quite literally all this engine does. The rest of it is very basic stuff: getters, basic setters, stuff that creates UI elements. The UI elements you can see here use the temporal. So for example, on this one, this gets called when we want to start a new project. So this gets called when you click the button to click a new, or to create a new project. And we create a new project menu, which is an object. And then on the temporal, we add a new event called onTrue, or using the onTrue method. And this is actually the first parameter here, what I've highlighted, and it effectively is a predicate. So once this is true, or on the point that this is true, we'll invoke this, which will be invoked when we call the temporal update method up here in the main method, or the main loop. But if we just look at this, actually, so basically when the new project menu can finish, we'll invoke this. Now, I could have used a method reference here, so I'm just going to change that right now. I don't know why I didn't do this. There we go. A bit better. When new project menu can finish, we'll do it. And this generally is how the rest of these work. Very simple. Yeah, I even did it below. So I think we can move on. So the next main class I want to look at is going to be the editor, which we showed above, and the engine. So this is created by the engine, and here we can see that the editor statically creates the brushes, which is important for something I may show later, but brushes have no state, and there's not a lot going on with them, but you can create them, or they're created here one time, and we use the same brushes forever. So then in the editor's constructor, we capture the engine and the display, and we create the undo and redo stacks, which are inappropriately named queues, but they're actually stacks, so I might need to change that. These are how we handle the whole do and undo idiom. We create a couple of UI elements. Well, actually, the 3 UI elements we saw. So the constructor doesn't do too much, so let's go to some of the methods we saw in the run method of the engine. The first of those being add editor events, which literally is a 2-line method. edit artboard on controls and undo redo on controls. Effectively what these do is, I'll just jump to them. The first one here, it basically will modify the current artboard, which is whatever artboard we've most recently moused over, if the conditions at the top are met here. So if the artboard interact control is pressed, which I believe is the left mouse button. Well, it is the left mouse button. If the current brush is not null and the engine is not, or the engine says that we're not hovering a UI element. So if the cursor is hovering a UI, you don't want to modify an artboard, obviously, even if the first two conditions are met. We then have we basically have an abstract brush class we use for all brushes, and each brush has a can use method which either returns true or returns true only if the brush would have any effect at all on the artboard. So as an example, you can't update the artboard if you try to change a pixel to a color that it already is. So you can't go from red to red because there's no change. So we just skip doing anything if the can use method returns false, which we actually gather that right here in this boolean. As you can see, both of these, the can use and the use method, take a bunch of parameters. The current artboard, the editor, and the index of the pixel that you clicked on. Using those four things, we can derive whether or not we can use the brush, and then if we can use it, we actually use it. Now as we can see here, when we call the use method on the current brush, which is abstract, this actually returns an event. And that's why we call it within the event push. So we event push whatever is returned by use. We'll probably look at that in a minute. That's very simple. This returns an event. We put that on a little event queue or event stack. Then if we actually look up here again, yeah, the undo and redo on controls, it just checks the undo and redo key controls, which are by default Control Z and Control Y, I believe. So you can redo something if you need to. We have these prelim controls, so that would be like pressing Control Z to undo something. So if the prelim key is met, then we can undo or redo. We have a second prelim 2, preliminary 2, which is shift. So if you press Control Shift Z, you basically undo things rapidly. Whereas before you would have to press Control Z, Control Z, Control Z to undo one at a time, or redo one at a time. So if we go back up to the top, we have handle events. And essentially, it just iterates over every event that's been added, and we post the event to the renderer if we should do that, else we just do it in the main thread. Now, it's a bit misleading because the renderer is single threaded, so it's not running in its own thread, which means that when you call the post method, even though we're not multi-threaded, the code just gets invoked right away, whereas otherwise it gets added to a list of things to do whenever the render thread can update. So these effectively are completely the same, both of these conditions. The only trick is, because the event is listed as a render event, it makes sure that it activates in the render thread. The beauty of this is that when I go back to engine and I make the display constructor take true here, then this would save me from having issues where code would be invoked in the wrong thread, because we check if it's in the render thread, or if we check if it is a render event, and if it is, it has to happen in the render thread. So one important caveat of this whole architecture is the problem of memory leaks. Your events, as we can see, are very long-lived objects because they get added to these queues and they live forever. They live until they're out of the queue. These are effectively your ring buffers of events. And matter of fact, I'm just going to open it. Yeah, you can see here it's just a linked ring buffer of a CS event, or a CSSS event. It's called queue, but it's actually a stack. Now, and then it's initialized at a size of 120. So an event will get added to this, either one of these. They're the same instance, same thing. Just one of them is used for done things and one of them is used for undone things. So you can continually undo and redo the same thing if you want. But the problem is that these things, an event will last until a size, or like 120 or whatever the size is, number of additional events have occurred, because then that event would be removed from the queue. So it'll last for a little while. And the important part of this is that you'll have what are kind of considered Java memory leaks, where an event is taking up memory. And it's not going to be freed even though it's not needed or going to be undone anymore. That's just part of the way that this works. So the flaw is, if your events take up too much memory, they don't get freed because they're still in memory. They're still in this event queue. Or this event stack. They just won't be removed for a long time. So what you have to do is allocate stuff for as little time as possible within the events. So the events are what actually modify things in the program, but they can't keep anything in memory for very long they have to allocate stuff for a very short period of time and let whatever the memory the event needs, it needs to be released by the time the event's methods are called or finished, or be out of scope. They cannot be cached. So literally beyond what I've shown, there's not much more to the editor. It's pretty simple, which I quite like, but we can now look at some of the parts that are more complex, in my opinion. Specifically, the artboard. So if we look at artboards, the artboards are the individual modifiable rectangles that you can create and color in during Sprite Studio. So the application is designed to allow for one or more artboards being alive at any given time. And artboards are all rendered with one shader, which I showed before, which is why it's called the artboard shader and why it's static. But before we look more into artboards, as you can see, it's quite a big class. We need to actually we need to understand how they are rendered. And the artboards are actually rendered with a paletted approach. So if we take a look down here, we create something called an index texture. So a texture which is the size of the artboard is created, which is essentially a 2-channel per pixel, 1 byte per channel texture. So we create 2 channels, so think like red, green, and each of those is 1 byte. What these pixels actually represent are not colors, but indices. So an index would be like a position in an array, right? These indices are actually indices into the artboard palette, which is here. It's actually passed in as a parameter and cached as part of the class. So these indices map to an actual color value because the palette will contain colors. The index texture will contain the index of the palette of that color. So you could think of, if I actually run Sprite Studio again really quickly, we can actually use the debug project, which just quickly adds a project. This is a 100 by 100 artboard, and every pixel of this artboard is not a color. It's actually an X and Y coordinate into a different texture which contains a color. And this is basically how rendering works in Sprite Studio. This approach of rendering, I believe, is actually how GIFs work. GIFs have a color palette, and the actual pixels of the GIF are not colors, they're indices into that palette. So below where we are at the beginning of the constructor, we basically create some simple stuff about the vertex array object for the artboard itself. Not too complicated, just some COLDSTEEL core abstractions, a vertex buffer builder, which takes some vertex attributes. What this does is set the size of the distance apart in pixels of the vertices in width and height. Initialize an actual OpenGL VAO and set it to be a draws elements, buffer it, etc. Now we need to jump to the artboard palette class. So The high level explanation of this is that it stores all colors that the user adds to any artboard. So when we open the artboard, when we create an artboard, we color it. The color values we want to put in the artboard are stored in this class. When a new color is added, its indices are returned to the caller. So when you call a method that adds a color, the indices that color value is located at within the palette is returned. So these indices can be written into the artboard's index texture at the pixel indices that were modified by the user. So if you click on a pixel, that pixel has some position within the artboard. It's like the pixel indices. We go to the channels of that pixel and write at it the the indices of the palette texture where the color is stored. And we can show all this in a minute. If we attempt to add a color to the palette that's already there, we will simply be returned the index in the palette of where that color is found. So the palette keeps track of the next place in its memory to put a color value, which it will return when a new one is added. We have two overloads of the put method, but neither is really used outside the class except occasionally. The main method to put a texture or to put a color in the palette texture is the put or get colors method. So if we scroll down to that method, it's right here. So looking at this method, we see that we iterate over the rows and columns of the palette texture, constructing palette pixels, which are pixels that contain actual color channel values, from a copy of the texel buffer that I keep on the CPU for faster rendering or faster reading. And obviously, if the color parameter matches exactly, which is found right here, if the color of the pixel we're currently at in the iteration matches the color we want to put in the palette, then we've found a match. Otherwise, we won't find it here. If we do find it, we can break out of this double for loop with a break label statement. The first time I've ever used a break label statement. And at the end here, so down here, we will effectively add the color if needed. So if we didn't find it in the loops, we will add the color to the palette. Now this actually is an O of 1 operation, this part, because we just index into that color palette and put the new color. So that's how we add stuff to the palettes. So the last thing to really look at here is going to be the palette pixel class. So it's actually kind of simple. It just stores channel values in a little abstraction, allowing anyone to read and get those colors, or the channel values. But what's odd, and what you may have noticed, is that we store these in longs. And you'll see other instances of this where we might use a short where you might expect a byte, or we used, in this case, a long where you might expect an integer at the most, 4 byte per channel color. The reason for that is obvious. It's because Java doesn't have unsigned types. So if we want to read this as an unsigned type, you're generally going to need to put it in a higher sized primitive. So that's why we use longs. But these are always stored as unsigned, which is why we have a channel values to unsigned method, which is very simple. What it does, whatever the types, however many bytes per channel, which we switch on here, we call the corresponding to unsigned method of that primitive. Unfortunately, we're not done yet because we still have, palettes are only half the battle, literally. We need to look at the artboard texture, which is right here. Luckily, a bit simpler. So like the artboard palette, this class offers a couple of obvious methods like puts, initialize, very simplistic. Flexible graphic is a class that I created that effectively just offers a byte buffer with the specified parameters, or that represents an image of the specified parameters. And the initialize method takes that graphic and the texture options and creates an OpenGL texture from it. Now, if we go down to the interesting part of this class, which is texel buffer, we will see that a lot happens in here. This method gave me a lot of problems, but it does do what it's supposed to do. Get you a region of an OpenGL texture. However, it does a lot more that I do not understand and had to fix for myself. For example, it needs the texel buffer passed to it to be 4-byte aligned. So this GL get texture subimage is what I'm referring to. And it takes a parameter called texels, which we can see is here, but it must be 4-byte aligned based on, I'm guessing because it just wouldn't work otherwise. That's why we create pixel size bytes plus 2 here, which pixel size bytes is going to be assigned to 2 right there, because index textures are hard coded to be 2 bytes per pixel. But we need to be 4-byte aligned, so we make it 4 with adding 2. From what I could tell, or at least, unfortunately for me, the GL get texture subimage, it seems to add a padding pixel at the end of each row of the subregion you're getting from your image, which is why we have to allocate a second texel buffer down here. If we look right here, fixed texels, which is exactly the number of bytes we need it to be instead of effectively twice as many. And we have to loop through the original texel buffer, just copying bytes over, but skipping the final pixel of the buffer we got with texels. So the final pixel of each row is padding, I guess. We skip it with this part right here, but other than that, we just copy. Then we rewind the buffer, free the original texel buffer, and return it. The beauty of this, why even do this, is that this method only retrieves part of an image, whereas without this one, you have to retrieve the entire image when you pull it down from GPU to CPU. So it's much more efficient, and more importantly, it doesn't use as much memory as its alternatives where you have to pull the entire thing. But if you're working with really large images, that may not be possible, so that's the point of it. But as you can tell, all of this is stored on VRAM. So the more VRAM you have, the larger your maximum project size will be. So on a high level, what the artboard does is glue all of that stuff together. It allows you to put colors in the palette, put colors in the index texture, which requires the additional indirection of figuring out whether the color is in the palette, getting its coordinates, putting those in the index texture, and it allows you, the artboard allows you to get subregions of the index texture. But that actually is most of this program. I can scroll down and you can see most of this stuff is not that complicated. It just calls methods from other classes which are a bit more complicated. So this is more of the outward API. But that really is most of the program. Obviously there are a lot of things I've left out, others I've spent too much time on, but I wanted to show some code, and I don't think there's too much more worth looking at right now. So where does this leave us? There are already a few really good options for pixel graphic creation. Sprite Studio is being created as an alternative, which offers most of the same features as current alternatives, as well as a few novel features. One major motivation for me behind pursuing this was to explore the concept of images as more than just visuals. What if images contained additional non-visual information whose purpose was designed by the creator of the image? For example, what if we treated an image as not only visual data, but also height map data? What if we embedded hitbox info inside an image? Textures in games are typically 2D images which have been uploaded to the GPU. These textures are available to shaders, which are programs that run on the GPU. If we upload the visual data of the image, we could also upload non-visual data as well, and we could use it within shaders. However, there are a few clear issues with this concept. The first is that currently it would be difficult to create an image that is not only color channel values, but also other info embedded or interlaced within the pixels. So we're essentially interlacing visual and non-visual data. And how do you actually create something like that? Another issue is that we typically use image file formats such as PNG when we create and export images for games. And these file formats are not designed to contain anything other than pixel data. This may well make it impossible to do what I've explained because there's no standard or really any way to interlace pixel data with non-pixel data, at least that I know of. Furthermore, supposing we overcame the first two issues, so we made an image that contained pixel data and non-visual data in a standardized file format, how do we actually use that data in our own applications? Do we break our loaded file into two smaller buffers, one containing pixel data and one containing non-pixel data? Or do we treat the loaded resource as one large image where perhaps the first 4 bytes of a pixel are red, green, blue, and alpha, and the following pixel or bytes are non-visual data? How does the GPU handle this? OpenGL doesn't have an easy solution to textures whose channels per pixel is greater than 4. So if Sprite Studio wants to fulfill its goals, it has a lot of issues to address. My ultimate goal with Sprite Studio is to create a program that offers unique features that other pixel art creation software do not. I want to be able to embed non-visual data on top of visual data in graphics created in Sprite Studio. I want to be able to easily create animations from images created with Sprite Studio. I want to be able to offer an easy way to create paletted images within Sprite Studio. And I want to create a sister library to Sprite Studio, which I may just call COLDSTEEL Sprites, which does all this for you. If you're a game dev or software engineer in general, you can use CS Sprites to integrate your Sprite Studio created graphics into your own applications with relative ease. Rather than creating your own metadata parser or command line tool to create animations from, Sprite Studio, or CS Sprites in particular, can do it easily for you. Eventually, I also want CS Sprites to offer a high-level way to access non-visual data exported alongside your images. You'll be able to write compute shaders and pass them to CS Sprites, which can serve as an API between your program and the non-visual data you created in Sprite Studio. So yeah, a lot of plans and a lot of time needed to implement it all. So I better get back to work.